Interesting.
Okay.
You're gonna be a YouTube professor.
I'm gonna be a YouTube star, influencer. Okay, Newton's law of cooling. So typically in heat transfer courses, you start with Fourier's law. Newton's law of cooling came, I think, about 200 years earlier, and his observation was that the rate of heat loss from a body is directly proportional to the difference between the body and its surroundings. So my understanding of his experiment was that he took a hot body, could be anything really, could be a bowl of soup, could be a roast turkey. If you've got temperature up here and time over here, it starts at some temperature, and he observed that in the first 5 minutes, the temperature dropped a lot, and then in the next 5 minutes, the temperature dropped a little bit less, and then the next 5 minutes, and it kept doing this, and it kind of asymptotically approaches whatever your ambient temperature is. So I think a lot of assumptions got baked into this, but he kind of figured, well, heat loss is proportional to, you've got a certain amount of heat in an object. As you lose heat from that object, that temperature reduces proportionally. So that's kind of the background. The big assumption is this direct proportionality, is they're saying that Q is proportional to delta T, where delta T is the difference between the temperature of your body at a given point in time and the temperature of the ambient surroundings. So 200 years later, Fourier got a little bit more precise. And one of the things that he was looking at that I don't think, again, I haven't read all the history on this. I don't think Newton really played around with the area variable as much, looking at sizes of different objects and understanding how you can normalize. But basically, Fourier's law says the same thing. Basically, Q is proportional to dt dx. So in words, if you've got kind of a finite difference in temperature, if you think about this as deltas instead of d's, you've got a finite difference in temperature over a finite difference in length, that gives you your rate of heat transfer. And because it's proportional, we can say there's just a proportionality constant. So more formally in Fourier's law, it is written as Q equals negative K dt dx. Why is K negative? Why do we need to have this negative in front of the K?
It's moving in a direction of decreasing temperature. So it's a negative, so it's positive.
Exactly. So if you've got a hot pot of soup and then cold surrounding, and that's not an example. If you've got a furnace and it's really hot in here, and then the outside wall of the furnace is much colder, if heat was flowing, if this negative weren't here, and heat was flowing upwards along the gradient, it would be flowing from cold to hot. What law does that violate? If heat spontaneously moves from a cold place to a hot place. Intuitively, we know that doesn't make sense, right?
Yeah.
Why doesn't it make sense?
Oh, it's has to do with entropy, so it's like a law.
Entropy, exactly. It doesn't violate the law of conservation of energy, which is the fun thing. Conservation of energy actually is not much of a restriction. So there is nothing that violates the law of conservation of energy to stop a bunch of heat moving from a cold part of a room to a hot part of the room, because you still have the same number of joules in the room. Does it violate the law? If the chair just started floating, I suppose you would be storing energy as gravity, right?
Yes.
It could spontaneously, because if I drop the chair on the floor, it would make some noise, it would bang, kind of waves of sound and heat energy would go out. So it's not in violation of the law of conservation of energy for all of that energy to just spontaneously get, sucked up into the chair and for the chair to jump off the ground again. But entropy says that's not going to happen. So entropy is the big restriction here. It's why thermal conductivity, if you conventionally have it as a positive sign, you need a negative in Fourier's law. Okay, so that's Fourier's law. It's linear. That's kind of the big thing that's nice, and it makes a lot of stuff in heat transfer easier. I know with like a lot of electromagnetic stuff, things are quadratic. So as you move further away from an object, things change quadratically. But heat transfer, that's not the case. Okay, so then we're starting with this law. This is just an observation. This is empirical. So from there, what we're going to do is we're going to develop that heat equation. I know we did the big multidimensional version in class yesterday. Today, I think we're just going to do the single dimensional and try to really drill that in, and then hopefully we'll kind of understand the multidimensional as an abstraction of that. So does anybody have an idea, just kind of moving from this, we want to develop that heat diffusion equation. And basically the assumption with the heat diffusion equation is, I suppose there are different heat diffusion equations. We're going to assume you've got some kind of simple one-dimensional thing, delta x, some small width slab, and you've got qx here, q evaluated at x plus dx coming out, no internal heat generation there. So what do we know from this?
This will somehow end up equaling that.
No, we're going to use this and this together.
Yeah.
So if you've got a certain amount of heat going through a wall because of conservation of energy, which is useful for some stuff still, what do we know about the other side of the wall?
They should be equal.
Yeah, it should be equal, assuming there's no internal heat generation, and we're going to assume that for now. So
Does the internal heat generation come from that energy generation thing that's in our long equation? Like, the
Yeah,
E constant?
exactly.
Okay.
Yeah, so later on we'll start playing around with examples where you do have internal heat generation. Those problems are pretty fun. My general opinion with this class is if you really get the calculus early on, then all that stuff we do later is very simple, because it's really just modifying things by one term and then following the math. So here, when you've got no internal heat generation, you've got qx equals q evaluated at x plus dx. And we know q, this is our term for q. So remember, this is a conservation of energy. This is first law. So it's derived from thermodynamics. This is just empirical. This is just an observation that Fourier essentially stole from Newton 200 years later. So we're taking this empirical observation, we're taking this first law, we're going to make a substitution. I'll check my notes. Just want to make sure we're doing this. Oh no, I'm sorry, I skipped ahead. Okay. Has anybody here taken real analysis? Okay, so in real analysis, there are all these really fun little tricks you can do. And I'm going to show you my favorite. And when you figure out if you're doing an analysis problem, actually, let me try to, I don't want to give away the answer. So, I started with jokes and now we're going to riddles. So on the left side, you've got q evaluated at x. On the right side, you've got q evaluated at x plus dx. So those are two terms that you often might see in something else, in the definition of something that you probably learned as a sophomore or junior in high school.
Derivative.
Yeah, the definition of the derivative. Does everybody recognize that we're partway there? Okay. So what we're going to do is we're going to put both terms on one side. You've got qx plus dx minus qx. What does that equal? 0. Are you guys not talking just because we're on YouTube Live? Okay, and now we've got 0 on the right, so we can divide anything we want by 0, and what do we get? 0, yes. What do you guys want to divide both sides by? What, dx?
Yeah.
Yeah. Yeah. Sorry, I'm going back and forth between delta x and dx, and that's not good formally, but intuitively this thing, they're very thin slice of x. Okay, and we go by dx on the right side, and that's still just equal to 0. There's a lot of this stuff in this kind of early heat transfer, which is fun. Okay, so now we've got qx plus dx minus qx over dx. So what can we do with that? And that equals 0. We're gonna take the limit of both sides as really should be as delta x goes to 0, but as dx. So we take this limit, and what do we end up with? You guys are so chatty in lab. You end up with dq dx equals 0. Okay, so we kind of threw a lot of math at this to explain something that we kind of already knew from the get-go, which is when you've got this simple slab with no internal heat generation, as you move in the x direction, you're not changing the total rate of heat transfer, right? What goes in must come out. So you can take different slices of the wall, and as you move along, you're not actually changing the total rate of heat transfer in the wall. Okay. Again, I just want to clarify, this is the no generation problem. Later on, we're going to solve what happens when, say, there's a resistor in the wall, or you're dealing with like a nuclear fuel cell, where as you move along the length of that rod, there's more heat in each step because you're essentially just generating heat. Not really generating it, you're converting it, because first lessons we're not generating it. Yes?
So Q is the rate of heat transfer, not heat?
It is the rate of heat transfer. It's measured in watts in metric. So it's a power term, not an energy term. Yeah. So in this class, the convention is, actually this is a good thing just to review. It gets different problems and good different textbooks, people use it differently. In this, Q is in watts. Q over area is Q double dash. Not double dash, double apostrophe. And that is in units of watts per meter squared. And then Q, I have to double check what we use for internal generation. It actually might be Q dot. I'm not sure, I have to double check this book. Sometimes it's Q dot, sometimes it's QG, but that ends up being typically in watts per meters cubed. So that's saying that in a given volume, you've got a certain amount of heat transfer. But the critical thing when you get to this stuff is you just really need to keep track of your units. You can't rely on the nomenclature to be totally consistent, especially when you move from book to book. But just make sure if you're dealing with something that's measured in watts per meter squared, you follow that through with your math and make sure that the units are correct at the end. Any questions? Okay, so we got dq dx equals 0. I'm going to erase most of this. I'll leave this up for now. Okay, so we've got dq dx equals 0. Now this is when we do that substitution. So we know empirically, negative, actually, sorry, it's negative Ka dt dx. So that's your empirical observation, and then we know for our generic thin slab problem, really any slab problem, dq dx equals 0, as long as there's no heat generation. And by the way, in the homeworks, when we say things like state your assumptions, these are exactly the things that you want to be mentioning. You want to really drill down, oh, this is predicated on known thermal heat generation. This is just empirical. Something else is predicated on first law of that. Well, this is predicated on first law plus known thermal heat generation. Okay, so we're going to make a substitution here. So this second line becomes d dx sub n negative ka dt dx n equals 0. Yeah. So by the way, just to back things up a little bit, what we're working towards right now is this heat diffusion equation, which just gives you a description of how temperature changes with geometry. And the cool thing about the heat diffusion equation is Q is no longer in it. So we would have like a complete description of temperature with relationship to X that isn't, you don't need to solve for Q to use that equation. That's what we're working towards. And so we just eliminated Q. And now we've got something just in terms of X, T, K, and A. So we're going to make another assumption here, right? And this is something we already know, right? Because the whole thing is predicated on this one-dimensional heat transfer through a slab. So the assumption, really two assumptions, is that K doesn't change with X and A doesn't change with X. So if you've got one-dimensional heat transfer through a slab, A is just constant, it's 1 meter squared or whatever. So this is a very good assumption if you're dealing with something like the wall of a house. And then K not changing with X is a good assumption for a homogeneous material. So our assumptions are 1D slab. And typically when you say slab and heat transfer, that's what people picture is kind of a flat surface. And then the other one I said was homogeneous material. So this would only apply to a single material, so it would apply to the fiberglass in a wall, but it won't apply to the fiberglass on the concrete and all that stuff because those things do change. Yes?
Does that have the same implications as the material being isotropic? Or is there a difference?
Isotropic, I think isotropic, what's the formal definition of isotropic?
I think it's, at least when we use it in class, I think it's that the K value is the same regardless whether it's in the X, Y, or Z directions.
Yeah, basically. I think isotropic is even more general than that because I've seen it used in other classes where isotropic also means like the elasticity doesn't change. Isotropic, because when you say isobaric pressure, tropic is, when it's used in thermodynamics, what does isotropic mean?
I didn't look it up, so.
Yeah, basically it does mean uniform. Having a physical property which has the same value. So it can be used in a lot of different ways. In this context, it's thermal conductivity. Other contexts, it's could be elasticity or something else.
No, I wanted to use this room for a class on Sunday. I just want to make sure that the boards are sufficiently big in size. That's all.
Not the best location, though.
That's okay.
Yeah.
Thank you.
Okay, so what we can do based on these two assumptions, the isotropic assumption that K doesn't change with X and the area doesn't change with X, is we can move both of these to the outside. Yes?
He mentioned something about assuming that it's an infinite wall. Is that for this kind of problem, or when do we assume that?
Yeah, so the reason that we assume the wall is infinite, which is a super silly assumption, is whenever you've got a finite wall, you've got corner effects.
Yeah.
So Q right in the middle of the wall is pretty much uniform, but then kind of at the corners, at the edges, you see something different.
How can we assume if it's an infinite wall, we have to know the area?
Oh, that's very good.
Wow.
You don't really assume it's an infinite wall. So the infinite wall is the kind of physical abstraction that you need for heat transfer to be one-dimensional. If the wall isn't infinite, it's hard to have truly one-dimensional heat transfer because of those corner effects. But that's a really, really good point. Yeah, so maybe instead of saying infinite wall, it's better just to say one-dimensional heat transfer through a slab, which tells you kind of the shape of things. Technically, you can have one-dimensional heat transfer through like a cylinder if you've got kind of an aside. We'll be dealing with this a little bit later. So we did all that nutty stuff with cylindrical coordinates. Most cylinder problems you'll be dealing with are, say you've got a fluid flowing in a pipe, it's warm inside the pipe, it's cold outside the pipe, you want to know how much heat is leaving, and in that case, all the heat transfer is radial. So it's only going in one direction according to your coordinate system, even though we know it's actually going in 360 degrees. We'll deal with that later. Okay. So we can take both of these terms out. We've got negative Ka d dx dt dx equal to 0. What was the thing I said before? 0 is on the right. You can divide it by anything, right? So we're going to divide it by negative 1, k, and a. We just strike all of that from the left-hand side. So now we've got d dx of dt dx equals 0. So this is a classic first-order differential equation. It's a second-order ordinary differential equation. Do you guys just know off the top of your head what the solution to this is? What's that?
It's been a while.
Okay, cool. We're going to do it then. How about this? Everybody take like 3 minutes and try to solve this. We don't have any viewers yet. I was hoping all my fans would be
Did
watching.
you send a link to the people with us?
But I've had a YouTube channel for like 15 years, so you'd think somebody by now would be. Oh,
YouTube hasn't existed for 15 years, has
It's
it?
existed for exactly 15 years.
Did it go in like 2007? I'm so confused.
Do they have-
Isn't it just a double derivative of t?
Double derivative. Yes. But so basically, we're trying to, when you solve an ordinary differential equation, you're trying to come up with an expression, in this case for t, such that that equation is satisfied. So if t, well, not just any expression, you want the most general one. So t equals 5. That's the solution. And we say dt dx. Well, does 5 vary with x? No, it's 5. So that's 0. So then d squared t dx, it's not really squared, also equals 0. Lo and behold, we've satisfied this thing with 5 as the answer, but it's not the most general answer. So while t equals 5 everywhere does satisfy this law, it's not going to be useful for a lot of problems.
So would t just be like the area of the slab that you're using in this case? Or like a formula for the area?
Is t the?
No, t is the temperature.
Yeah.
But like, I know you're saying just plug, if you can plug in 5 as a general answer, but like,
Basically, what we're trying to come up with is a general expression for t of x. So the most general way that t can vary in one dimension along x. In this weird infinite wall that somehow also has an area to it, a finite area. Okay.
Isn't it just a line?
It is just a line, yeah. So basically, do you guys want me to expand this out and do it?
yes, please.
Okay. So you bring dx to the other side, and you get d dt dx equals dx. We're going to take the indefinite integral of both sides, and you've got dt dx. Am I writing too quickly? Is this still legible?
If you're multiplying by the x on the right side, wouldn't that give you 0?
Yes. Thank you. So it's 0 dx, which is 0. So dt dx. So when you integrate integral of 0 for any indefinite integral is a constant, right? Yeah, so C1. Do the same thing again, bring dx up to the right, integrate both sides. Now we've got a constant here, C1 dx, so what we're gonna do is get t equals C1x plus C2. So as Francesca said, yes, it's just a line, right? This is slope, intercept, it's a line. C1, C2 are not that interesting, so we're now going to add a little bit more detail to the problem, and we're going to apply some boundary conditions. So we're going to say at x equals 0, t equals t1, and at x equals, you guys want to use L or D for the width of a slab? L? Or use L? X equals L, T equals T2. We haven't really lost generality here. We're just saying T1 and T2, they can still be anything. So we're going to apply these boundary conditions. And basically what you do is you just plug them into here. I'm going to erase this now because I got kind of a knee thing and I don't want to bend down or right on the board. So the first BC, first boundary condition, is T of x equals 0 equals C1, we're plugging in 0 for x, plus C2. Oh, and sorry, and that T of x equals 0 is T1. So first boundary condition is T1 equals C1 times 0 plus C2. So that first term goes away because it's something times 0. So now you've got T1 equals C2. And then the second boundary condition is at x equals L, you've got T equals T2 equals C1 times L plus C2. And now we know C2 is equal to T1. So we're just going to put T1 here. And we just rearrange because we're just trying to get an expression for C1. So now bring T1 over to the left-hand side, T2 minus T1, and we'll divide both sides by L. Sorry if I've skipped a step here, and that's equal to C1. Do you guys see what I did there?
Yeah.
Yes, everyone nod. I've got 2 nods, 4 nods. Okay. So now you've got an expression for C1. It's T2 minus T1 over L, which basically just describes the slope. So now we've got an expression for C1, an expression for C2. We're going to plug them back in, and our general expression for T is T2 minus T1 over L all times X plus T1. So basically in this slab, at X equals 0, you start with temperature T1. It increases linearly as you move from X equals 0 to X equals L. And when you plug in, sorry. Oh, that was from outside. When you plug in L here, these two cancel out, and you've got T2 minus T1 plus T1, T1, T1 cancel out, and you just got T2. So basically it is just changes linearly from T1 to T2. By the way, we don't always note this, but it should be understood that this whole thing only applies for X between 0 and L. You guys familiar with the set notation? Technically, actually, it's a continuous thing, so it's probably could be like brackets.
Why is the slope positive and not negative?
Why is the slope positive?
For the
In the
diagram
diagram?
that you drew.
Oh, because we want, well, actually, yeah, I mean, by convention, we should have T1 is higher. I'm going to redraw this. Yeah, intuitively, we're thinking of, technically it all still applies and you would just have a whole bunch of stuff be negative, but intuitively you're absolutely right. You've got Q is flowing from this hot part T1 to this colder part T2 as X goes to L, 0 to L, and yeah, decreases linearly. That's a better way to think about it. Thank you. Yeah, and this is, you just want to clarify, this is the domain of the function. At x equals 2L, we don't really know anything because we've only looked at this one slab. We don't know what's outside the slab. Okay, now we've got a general expression for temperature in a slab. Let's just remind ourselves of the assumptions. What are our assumptions? Call them out.
Homogeneous material.
Homogeneous material, what else?
Infinite wall.
Infinite wall, which is basically another way of saying one-dimensional heat transfer. What else?
1D slab.
We just said that one.
Linear temperature difference.
We arrived at linear temperature difference based on these other things. But another important one is no internal heat generation. I think that's the last one. And of course, first law of thermodynamics, right, tells us that energy in equals energy out. Second law of thermodynamics really is just a convention thing, but that's what gave us the negative sign. I think those are all the assumptions that got baked in here somewhere. Okay, let's box that. This is an important conclusion. Okay, we have 20 minutes left. Yes. Thermal resistance. Okay. So,
Could you
yes.
explain a little bit what determines the K value?
What determines the K value? So that's something Professor Burke knows a lot more about than I do, because he's really more of a thermomaterials kind of scientist. So like I only learned from him this class, but you know how metals are tend to be very electrically conductive. They're also very thermally conductive, in part because metals have this kind of electron sea. You guys remember that? I don't know well enough to explain it in much more detail than when all the metal molecules go together, the electrons are kind of free to float about, and they're able to transfer energy. You know, when you're talking about gases, it kind of makes sense that, I'm going to erase this. When you're talking about gases, it makes sense that when you have a higher density of particles, you get higher thermal conductivities. Because if you're in kind of a vacuum and there's just a few particles, it's very hard for energy to transfer from your one wall. This is, sorry, I'm kind of cheating the problem, but this is a different problem where you've got a gas between two walls at different temperatures. So if you've got a wall that's hot over here, we've got a wall that's cooler over here, we're going to assume this thing is very tall. If there's not that many particles to transfer energy. So that kind of thing would determine the thermal conductivity of the gas. When you've got more particles, you've got more energy carriers. With solids, I don't know, it's all kind of like a molecular thing. I think it has to do with how the molecules are meshed together. So things like diamond, where you've got this grid of carbon molecules, or graphene. Incidentally, if you want to learn more about graphene, the guy who wrote the book is like across the hall. Graphene is this single molecule network of carbon. I think that's what it looks like. So they're really good at transferring energy, those carbon molecules, because they're all kind of connected to each other. So that's basically what tells you thermal conductivity. Now, I used to be a practicing engineer. So what tells me thermal conductivities is ASHRAE Fundamentals 2013, which has a great reference table in the back that says if you're doing gypsum board and glass and this and that and the other thing, these are your thermal conductivities, and that's how you get your resistances.
So are they like empirically determined, or can you like do some?
It's empirically determined and scientifically justified. Like most things, you kind of observe it. I mean, that's what science is, right? You're observing and describing the universe. So you observe that a phenomenon is the way it is, and you kind of explain what's going on. With some exceptions, there are some very few phenomena are created, right? Heat transfers pretty much always exist in the universe. There's some like nuclear and plasma stuff where if you really think about it, probably didn't happen a lot until people started making it happen in the lab, but that's really the exception. Okay, so we've got this general expression. Oh, any more questions before we move on? We've got this general expression for temperature in a generic slab. So there's a notion, we talked a little bit about this in class, thermal resistances. You guys kind of touched on that, right?
Yeah.
Does anybody want to tell me a little bit about what they know about thermal resistances, why they're a useful tool? So if I'm working on a project, I used to be a heating, ventilation, air conditioning engineer. So we had buildings, right? You design the wall of a building, and your wall of the building could have, gypsum board, and then there's 2x4 wood here, and maybe there's a thin insulation layer, and then there's like a very thin layer of aluminum siding, something like that. Okay. We want to make sure that this building is going to meet code and is not going to have some unmanageable heat loss under different conditions. So we would run two different tests, right? We want to know at a hot temperature how much heat, when it's hot outside, how much heat is going to be gained through those walls. And we want to know at a cold temperature how much heat is going to be lost through those walls. And we use those two numbers to size the boiler and the air conditioner. Or I guess the air conditioner and the boiler in that order. So something that's useful is if you can describe the wall in terms that wall temperature, if you could kind of abstract the wall into something that's independent of temperature, then you can just apply different temperatures to that wall element and you'll know how much heat will transfer. So we want kind of a generic way of describing the wall that's independent of temperatures actually being applied. The other thing that we'll find that is really useful, what we're going to do is when you start stacking up different elements, it's very easy to add these thermal resistances together. That's what we're going to be doing. We're going to be kind of deriving thermal resistances. So that's the motivation for what we're about to do. And I hope that keeps you guys interested enough to follow me with the math. It's always hard when you don't quite know where the math is going and it's just math on the board. To get thermal resistances, we are going to go back to our original Fourier's law. Q equals negative Ka dt dx. We've now got a generic expression for T. So if we want to make the substitution, we can write Q equals negative Ka, and then what's dt dx?
T2 minus T1 over L.
T2 minus T1 over L. So this is your expression for Q. Once again, with all the assumptions baked in, we should get like a course going where we practice saying all the assumptions again. 1D heat slab, 1D heat transfer, infinite wall, whatever that means, homogeneous material, no internal heat generation, all that stuff. With all those assumptions, this is your Q. So what I see here is there's this temperature difference, and basically all we're going to do is a little bit of algebra to try to break out a term that's independent of temperature. So the first thing is we've got a negative here, we've got a binomial here. So if I want to bring this negative into here, so I don't have an extra negative out front, what does that change? How does that affect the binomial? Flip something, exactly. So Q equals Ka times T1 minus T2. Remember kind of the convention that we assumed is T1's higher than T2. At least that's the intuition you should be working with. I think the math is the same no matter what, but think of this as this is now a positive number, right? T1's higher than T2. The other thing we're going to do is we're going to bring this Ka down, which seems like it makes it to an uglier fraction, but it's going to be really useful. So we're going to write T1 minus T2 equals over L over Ka. Okay? I know that this, since you guys went through algebra, this is like ugly, right? This is an expression that's asking to be simplified, but we're not going to simplify it. We're going to leave it like this. So now in words, what we have is your rate of heat transfer through this wall with all these assumptions is equal to the temperature difference, the hot minus the cold, divided by this L over Ka. And this expression here is called a thermal resistance. You guys are taking Intro to Electrical Engineering this semester, right? No?
I think a lot of people took it.
You guys have already taken.
Oh yeah.
Yeah, okay, so
But most
two
people have.
of you have taken it, 2 of you are going to take it probably.
I already
right?
took it.
You already took it. Okay, you're going to take it.
Yeah.
It's exactly the same as electrical engineering. That you've got thermal resistances, you can stack them up in series. They act like a series circuit. You can stack them in parallel. They act like a parallel circuit. It's like a perfect analogy. It's a perfect analogy predicated on these nutty assumptions that we have about infinite materials and one-dimensional stuff, which isn't really true. And you start to see that when you get to really complex things where you really do have three-dimensional. We'll do that later. This is your thermal resistance. And basically, the point is once you've defined the thermal resistance for a material, so I know I've got a piece of gypsum board, I know it's 1/2 inch thick, I know the thermal conductivity, I know the area, that applies whatever temperatures I plug in. So I can plug in its 20 degrees Celsius inside, that's about room temperature, 0 degrees Celsius outside, that's about freezing, it is freezing. I could plug in its 35 outside and 20 inside, and I'll get different, different direction of transfer, but I can compute it all. So that's thermal resistances. That's the first reason thermal resistances are useful, is you're describing the material independent of the temperature difference. The second reason is when you start stacking up materials, like I showed you here, where you've got gypsum and wood and insulation, all these different things, you can stack the thermal resistances. And we are going to demonstrate that that works. So we're going to take, this is our example before where we have a single material. We're going to put another material on top of it. And down here, it's going to be T3. Different angle because it's a different material, and this one, I guess, is a little bit less conductive. Just double check my notes. So, yes. So we're going to draw a thermal circuit abstracting this material. And I'm sorry if I keep hammering this in too many times, but I really do think it's important to go back to the assumptions. So this thermal circuit that we're drawing right now is based on one-dimensional slab, no internal heat generation, all these things. When you start adding those things in, this goes out the window. So don't try to, down the line, don't try to model internal heat generation as like a resistance and also adding heat in. That thermal resistance only applies when there's no internal heat generation. So we're just going to label this R1, and this is R2, resistance 1, resistance 2. Resistance 1, we're not going to really use this right now, but it's L1 over K1 over A. A is the same for both. That's really important. But this is some length and some thermal conductivity. R2 is some other length, some other thermal conductivity. For brevity, we're just going to keep them as R1 and R2. I'm going to move back to the side of the board. Everybody have this? So the heat transfer from point 1 to point 2 is what? Point 1 to point 2.
If you repeat the question, sorry.
What's the term for our heat transfer from point 1 to point 2?
Is that Q1 minus T2
Over R1. Okay, what about the heat transfer from point 2 to point 3? What's our expression for that? T2 minus T3 over R2. So what I'm going to do for both terms is I'm just going to multiply each side. The top term is going to be R1 on both sides. Is everybody okay with that? And then R1 cancels here. Same thing, R2. I really hope the math doesn't get away from the intuition too much. It's good to know what's actually happening in the background, but and kind of why the things work the way they do. R2 becomes R2. So just a little bit of algebra. And now we've got T1 minus T2 equals R1 times Q 1 to 2. And T2 minus T3 equals R2 times Q 2 to 3. So now we're going to add these two together. R1 Q 1 to 2 plus R2 Q 2 to 3 equals T1 minus T2 plus T2 minus T3. What can I do on the right-hand side?
Get rid of the T2.
Get rid of the T2s. What can I do on the left-hand side? What do we know about those two Q terms?
What they're equal to?
That they're equal to each other, yeah. Because we know that if a certain quantity of heat or a certain rate of heat transfer going through this first slab, there's nowhere for it to go but through the next slab. Because we've got an infinite wall that also sometimes has a finite area. So we're going to replace both of these with just the term Q. And then we've got R1Q plus R2Q. So we can take Q out. And we've got R1 plus R2 times Q equals T1 minus T3. And now we're just going to bring this back to the other side. Now we're going to say Q equals T1 minus T3 over R1 plus R2. So all we've done now is we've shown that this thermal circuit analogy, series circuit, series material, it applies, right? If you've got a bunch of different materials stacked up with different thermal resistances, you can just add those thermal resistances together and you'll end up with some, equivalent. So for building, you add up your gypsum and your plywood and whatever else, and you've got some R value for the wall, some big thermal resistance. This, by the way, thermal resistance is in units of Kelvin per watt. All right, yeah. So you've got temperature up here, Celsius, Kelvin, doesn't really matter because you're doing a temperature difference. So it's Kelvin over watts. And when you divide, you end up with watts, which is what we wanted. When you talk about R values for a wall, units are a little different. So if you've got like a really heavy duty wall with insulation, you might have something like R20. That expression takes out area. It's also, when you say R20 in the United States, you're using imperial units, so like BTUs and feet and stuff. The concept is the same, that basically you've come up with some kind of all-encompassing single value that describes the heat transfer properties of the wall independent of the temperature, and you can use that. Now, I mentioned this in class yesterday, and I just want to kind of throw the caveat out on the board that when you have big temperature differences, the thermal properties do change. So there'll be some appendices in your book specifically for metals, which tend to operate at a whole range of temperatures, where if you've got steel in a furnace, you will have different thermal conductivities than steel at room temperature. And actually the cool thing about that is you end up with anisotropic behavior, not isotropic. So I don't think we're ever going to touch this in this class, but if you imagine you're working on a nuclear reactor, I hope we don't deal with nuclear reactors, at least not in person in this class. And you've got a really thick slab of steel, you could actually imagine the properties would change as the temperature changes throughout, which is cool, but not relevant, except for it's just a good thing to know, kind of always know where your assumptions come from and where they break. Okay, so that's thermal resistances. The last thing I wanted to say is we've been doing thermal resistances for materials, just solid, intuitively we're thinking about solid slabs of things. If you go back to where we started class, I'm gonna get rid of this. What came before Fourier's law? Newton's law of cooling. H8 delta T, make it T1 minus T2. This is Fourier's law. We dealt with it, or sorry, Newton's law of cooling, we dealt with this a little bit. H is your heat transfer coefficient. So it describes, what are the units for H? Do you guys remember that? H is in watts per meter squared Kelvin. I will say that heat transfer coefficients for convection, typically you use this when you're describing convection, are incredibly enigmatic and inconsistent. So like there are all these incredibly complicated models where if you've got a room of a given size, you can say that average internal heat transfer coefficient is 6, but it could be 20. It's like, it's the reason that thermofluid scientists still have jobs, because it's really hard to just simplify and just pick a number and have it actually apply. The critical thing you can do with convection is you can make a thermal resistance too. So we can just bring, and this should be even more unnerving to you as people who are used to simplifying your fractions. Oh, I'm sorry, it's T1 minus T2. This feels like a sin. Doesn't this is wrong. But this is how you get your convective R. And we can stack these up in a thermal circuit in exactly the same way that we would stack stack physical objects. So if you've got a really simple wall that's just gypsum board with with L and thermal conductivity K, and then on the outside you've got H equals 20 watts per meter squared Kelvin. On the inside you've got H equals 6. Your equivalent thermal resistance for that wall, it's just 3 resistors added up, right? So it's R equals 1 over plus HI, 1 over HI A plus L over K A plus 1 over HO A. I'm sorry, my handwriting has gotten worse over the course of this hour.
Do those H values say like 20% and then K, or what is that? Like H0 on the right says 20% and then there's something.
It's like 20 watts over meter.
Oh, sorry, 20 watts per meter
sorry.
squared. No, this is my fault. 20 watts per meter squared Kelvin. By the way, this Kelvin, it always is a temperature difference. It's not an absolute temperature. So it could be, you could just as easily write it degrees Celsius. Differences in degrees Kelvin are the same as the differences in Celsius. Or in degrees Celsius is the difference in Kelvin. I think Kelvin, you don't actually say degree. There's a lot of formal stuff that I'm probably not going to do right. So like, I think I was supposed to start with deltas and then go to Ds. And, you know, I do have a BA in math, and I hope they don't take it away. They might. Yeah, so thermal resistances are really useful because you can kind of describe things. I'll just add that under extreme circumstances, the thermal properties of materials, physical hard materials, solids, do change a little bit with temperature. Heat transfer coefficients change a lot. So we will say, oh, the external heat transfer coefficient is 20 watts per meter squared, and the temperature is 5 degrees Celsius. And then we'll say, okay, well, what if the outside temperature is 0 degrees Celsius? This H equals 20 will kind of the velocity of the fluid near the wall. So this is a bold simplification, but it's a very useful one for now at least. And later on, we'll really interrogate these coefficients. I think that's everything we have time for today. The one other thing I wanted to play around with, and maybe I'll try to put a problem on the next homework about this, is when you're dealing with thermal circuits, you end up with kind of big changes in magnitude. So if you had just like a simple aluminum panel as your wall, you really can't neglect those resistances created by your convection coefficients. And if you did, you'd get totally wrong answers. Like if you had an aluminum wall and it was cold outside, and you said it was 20 degrees inside and 0 degrees outside, and you assumed that these were the surface temperatures on either side of that sheet of aluminum, you would get completely unrealistic rates of heat transfer. When you factor in, oh, but there's kind of an air barrier here, and there is this extra layer of thermal resistance created by convection, that really matters in this case. In other cases, it doesn't matter so much. So with contemporary high efficiency buildings, we pretty much never relied on thermal resistance from that convection coefficient. So if you wanted to build your wall to R20, to some standard of high thermal resistance, you would make sure that wall from surface to surface had that resistance. And if there was a little extra resistance because there was an air barrier on the inside and that created a little extra, great. So I would have loved to do a numerical example there. I'm afraid we didn't have time. Okay, any questions before we wrap up? Okay, cool. I'll see you guys on Tuesday.
Thank you.